Okay, so welcome back. We have now the first lecture of the second mini course that we're going to have throughout the week. I just want to have a few words before that. First of all, registration. If you have not registered yet, you can do it throughout the day. It's open there, so you don't need to do it now. I mean, you can do it later. And we're planning to have a lunch, a special lunch on Wednesday. If you want to be there, just go to room 205 or 208 on this floor there, or in the registration desk to pay your contribution for the lunch, right? It's, all right, so what else? Oh, we're going to have a cocktail at the end of today's activities. We'll be just outside. You're all welcome. It'll be very nice. Okay, so let me introduce the lecturer for the second mini course. It's Farbod Shokrieh. Shokrieh? Good? Okay. From Washington in the United States. And the title of his mini course is Berkovich Spaces, Tropical Geometry, and Number Theory. So please, Farbod.
Thank you. Thank you for the introduction. Two questions. Everyone can hear me well? Should I not yell? And is this large enough? Okay, thank you. Thank you for the opportunity to speak and the generous time. I should start with some disclaimers. The title, I think, was picked by the organizers. It's a long laundry list of things. And I realize the background of most of the audience, apart from some experts, is mostly in combinatorial side, so I will do my best to make the lecture self-contained, but that also means that I will not say many things about things that are not combinatorial. I'll start with the outline of the lectures. The outline is rough in the sense that if I get a feedback, both by looking at confused faces, or explicitly, if you tell me something you would like to hear more, I'm happy to adapt. I have 4 lectures, so I can hopefully change the later lectures. So the outline, this is a rough outline. Today, I will mostly talk about some motivations coming from number theory. So more explicitly, I'll say mostly heights. But in the background is Arakelov geometry, which I won't really do justice even giving an introduction, but I'll try to say something towards the end of my lecture about how the heights theory could be interpreted in more geometric way. And then tomorrow, it will be Berkovich spaces. Again, I won't do justice, but I hope I do some explicit examples and the view of tropical geometry from the lens of Berkovich spaces, which gives me, so it's true that tropical geometry has analogies with algebraic geometry, but for number theory applications, it would be nice to have a machine that takes number theory, brings it to combinatorics. So Berkovich spaces gives the sort of a very convenient framework and strong set of analytic tools to do that. And then most of Thursday and Friday lectures would be combinatorial, so connections between 1 and 2, so how to use tropical geometry or Berkovich spaces to address questions in, say, heights theory or number theory more general, so connections between 1 and 2, more explicitly using 2 to address 1. And it has the maybe pleasant aspect that things get easier in the sense that towards the end it will be more explicit. So today I apologize for pretty much everyone. Experts in the audience would be bored by seeing heights theory, and for some of you it will be the first time seeing it, so I apologize from everyone that you have to bear with me because I'm in a difficult situation. Anyway, all that being said, let me start by some very basic. And again, I have promised to keep the lectures quote-unquote self-contained, so please feel free to interrupt me if I'm losing you. So there is a there is a way in which I hope you all agree that 1 and, let's say, 1,000 divided by 1,001 are different. I mean, not only they are not equal, but even though they're very close to each other, the second one is more arithmetically rich. And you might want to capture that quantitatively. You might want to have a notion of complexity that says, this is exactly how much more complex than this. And for that, actually, it's very intuitive. You can define height of a rational number. Let's say, well, the definition I'm going to give, it's going to already take care of the fact that you can always think about reduced form. You can define it as the number of bits needed to store A over B on a computer. And this is a perfectly good definition, actually. It's actually a mathematical definition. You can define it as, so this can be max of logarithm, maybe base 2. Base is just a constant of absolute value of A and absolute value of B. The biggest one is the number of bits that you need for your memory, right? This might look ad hoc, but in fact, it's perfectly fine. I'm going to immediately go to more interesting varieties. So you can think of what I was doing as P1. A point in P1 can be given with a tuple A and B, and you can represent it by a rational number. It's like the slope of the line for Pn. So let me move to number field, a finite extension of Q. Just, it's perfectly fine for the entire week to think of just Q. Already things that I'm going to say are interesting for Q.
Why is it max and not the sum? Because like A and B could be like completely independent.
How many bits of information you need to present it? So if you have, like, if the number here, I guess, what's log of 1,000 base 2? 9, 10 bits. If you have 10 bits of if you have 10 bits to store, then you can represent this number, right? You just write them in base 2.
Why is not the sum?
The size of the memory that you need. I mean, it's up to, I guess you're talking about the number 2 here is the problem. You need 10 bits is really enough. If I put a 2 here, you would, already I'm ignoring a constant here. So if I put a 2 here, I think you will be happy. Everything, it's going to be worse. It's going to be, everything is going to be up to a constant. Yeah. Let's get to more fancy stuff, and this will be nothing. Soon things get worse, but the message is that for certain varieties, things get better. So you can define a height function, so-called naive height function, for points in projective space, which I will represent by a tuple, which is only well defined up to scaling. As again, I can write the same thing, maybe because I have a field extension for compatibility reasons. I divide by, so an element in K can be also thought of as an element of the extension, and I want to be worried about compatibilities. There's some scaling, but I write the same thing. Needed to represent a number on a computer. I realize this is, some people get really annoyed with this, so let me write a formula which is not crucial for my lectures. You can define it more mathematically. Let me write the formula and then say what each thing means. And then you want max of logarithm of So for your number field, let's say in the case of Q, you have all the prime numbers you have to worry about and something called Archimedean place. So you think of this as for all absolute values that you can put on Q, the p-adic absolute values and the usual absolute value. And you have to look at the maximum of the adic absolute value of each entry. And it turns out this is well defined. Of course, you should immediately be worried about that. This is only well defined up to a constant. You can multiply everything by 2. How is that OK? But it's OK. There is some product formula which is essentially for Q is unique factorization that allows you, if you scale things, the contribution is going to add up to 0. Anyway, I don't really care about this formula. Just you could write it mathematically. And there's something called Northcott property, which is the key for usefulness of the height theory. And Northcott's property, which says if you bound, in this generality, let's say for now, if you bound the degree of the point, so if degree of the point is bounded by d, and the height of the point is bounded by some b. So degree of the point is, so I guess you look at the field generated by these numbers. That's a finite extension and degree of that field extension. If you bound the degree and you bound the height, which is the number of bits that's needed, then you have only finitely many choices. So it's a finiteness result. So the size of this set is finite. And even if you are not number theorists, you should probably know that in Diophantine equations, finiteness questions are quite important. There are only finitely many solutions to this Diophantine equation. Sometimes even you get Fields medal for it. Falting's theorem, which is related to the stuff that I'm going to talk about, is showing that curves that are of genus at least 2 will have finitely many rational points. And a crucial ingredient of various proofs of that, or the proof by Faltings and the proof by Vojta, which is quite different, uses height theory in a crucial way. In fact, one of the functions that I will discuss today is a key ingredient. So height, let me just say the mode of heights are important for finite questions, finiteness questions. Height functions are useful for finiteness results. But even beyond that, already for BST conjecture, there are sort of quantities that come from height functions. Yes?
A stupid question. A's are integers in that?
Not necessarily, but I mean, I said if you're working over Q, you can always scale and assume it's integer. And I said the representation doesn't matter because of the so-called product formula. Unique factorization gives you. So even if you're in a number field, you can always assume it's an algebraic integer. You can always clear denominator. But it's really not important. This definition doesn't care. OK, so that's very general so-called naive height. Now I want to talk about height machine, which is sort of so Andre Weil, I believe, was the first person that wrote this systematically. Maybe before doing that, so the Northcott property, I'm not going to give a proof, but it's not a deep, super deep fact. It's actually quite elementary. You can do it in second week of a number theory class. But I hope it's also clear from this example. If I just bound the number of bits you have, there are finitely many numbers you can write down, right? It's not that difficult.
But with that interpretation, we wouldn't need to bound the degree, right?
Yes, so if you want, you can think of examples like this, that if I don't bound the degree, all these have height relatively small, but there are infinitely many of them. So this is the optimal version of Northcott property. Okay, my next goal, or the height machine, wants to take this sort of relatively elementary height function and take it to maybe more general varieties. Maybe you have a more complicated situation. You have a bunch of equations that you might worry about the finiteness of the number of solutions. So I'm going to start with a nice variety, let's say smooth projective variety. In fact, my main example later this week will be abelian varieties, and later today. And already, if you're, I'll say something about abelian varieties, but in dimension 1, elliptic curves. Which is the very interesting curve that you can write down, which is not only a curve, it's also a group. And abelian varieties are higher dimensional elliptic curves. Since I said projective, I can put it inside projective space, but I have to make some choices. And I want to say what choices I will make and what's the dependence on those choices. And then it turns out for abelian varieties, which is the prime example I will worry about, things get much nicer. So it's projective, which means almost by definition, you can put it inside projective space. But you can do it in very different ways. Given any map inside projective space, you can guess what I'm going to do. I'm going to say, if you fix the map, you get a height function, because you can put your point inside projective space, and I told you what is the function. So it's just composition. You can define h sub phi to be the composition of the h, this h, with phi. So I have to use phi first and then take the height of that point. Okay, but I mean, I fixed the map. That's not very clear how I would do that. If you know a little bit of algebraic geometry, you know you can do this if you have an ample line bundle or divisor. So ample means some multiple of it is very ample, which means you get a map into projective space. So you can use this ample divisor. You make a choice here. Not only I made a choice for my ample line bundle or divisor, I make another choice what power of that I should pick. But nonetheless, I get a map with all these choices and put it inside projective space, and then I get a height function. Okay, you should be uncomfortable that all these choices should matter. So I can define a height of a height function for the variety x with respect to this divisor to be 1 over n, this phi of nd. And you must be upset that this definition doesn't have an n in it, but the notation should have an n in it, but I haven't put n in it. I'll address that soon. Yes?
The n of projective space is different from n of.
Thank you. Yes, but you did that in your lectures too, so you should forgive me of all people. Not n, for f you reused it.
Oh, yeah.
But this is more horrible. Thank you, m. Yes. Technically, yeah, you had different boards. Thank you. It's just a notion of complexity. I mean, other notions of complexity also you get, like entropy is also a non-integer that captures the complexity of a dynamical system. So it's, you just get a real number that says how complicated something is. And if a real number is bigger than another one, it means that it's more complicated. There is no, I don't think I have a better answer than that. I don't want to restrict myself to integers as my notion of complexity. Already for the example that I erased, the nth root of 2, really you will end up to having all sorts of denominators. And it's actually closely related to something I'm going to say. It's a major open problem for some very basic function, which I will essentially define. Whenever that number is non-zero, people don't know what kind of number it is. Is it transcendental? Is it algebraic? Nobody knows. Yes. Yes, if this is M, have I messed up anywhere else? I think it's all okay now. Okay, let me say one more. Maybe if these any line bundle or divisor, any divisor, you can still get a height function because there is this little trick that you can write d as d1 minus d2, both of which are ample. There are different ways of doing it, but you can say, for example, d1 is, let's say, mh plus d, m large, h ample. Then you can, this will be ample, and d2 is minus, d2 is mh, which is also ample. So you can write it as difference of two ample divisors or line bundles, and then you can define hx sub d is hx d1 minus hx d2. What I'm trying to say is that for any line bundle or for any, not only ample ones, but even non-ample ones, you can have a height function. And I'm getting to this dictionary between geometry and arithmetic very soon. So the upshot maybe, just to summarize this little discussion, is that for any divisor D or line bundle, on X, there exists some H sub D, which actually takes geometric points to real numbers. And it satisfies some nice properties, which I will come back to soon, satisfying some nice properties. One desired property is, of course, the Northcott property I've said, but you might want to care about positivities and things like that.
You are ignoring choice of coordinates on here.
I'm ignoring many things, but you can, I've also made a choice of the basis for my space of global sections, which is the coordinates you're talking about. Yes. And I have already said that you should not like this, but I will justify it's okay in a moment.
If you change coordinates, it's up a multiplicative factor.
Yeah, actually, the next fact I want to say is going to say that the issue of all the choices I've made is somewhat controlled. It's not going to be super satisfying, but it's the best one can say in full generality, and then I'll make it better for abelian varieties in a second. So here's a fact. Again, not super deep. I've taught it in a class. But so here's a fact that's trying to address all the choices I've made. If these are already very ample, you already have, without a choice at least of the multiple, you already have phi sub d from x to Pn. Okay, you make a choice of basis, but let's move on. Then the fact is that h sub d that comes here, I can also look at the multiple of d, m times d, and get a height function according to the first board to the left. It turns out they are essentially equal. Now I have to use the notation from there. But the crucial point is that this is up to a bounded function which somewhat annoyingly people use the sort of computer science O of 1, but it's kind of misleading. Bounded function in what? Bounded. So it depends on everything. It's bounded as x varies in capital X of k bar. So so there's an equality up to a constant, where the constant is bounded as you move around in your geometric space. Okay? Which ends up translating into the fact that that definition is only well defined up to a bounded constant. Again, bounded means as you move in your, as you move your points. It depends on all sorts of things, but it doesn't sort of, as you move in the space, the difference between the two functions cannot explode. It remains bounded in a precise way that I'm talking about. And then there are other things maybe I don't write, but if D1 is equivalent to D2 or line bundles are isomorphic, the functions are essentially again the same up to a bounded function. So everything is up to a bounded function. I'm going to write this a little bit more fancy and more digestible, which has actually more information, even though it's shorter. So the theorem, essentially due to and away, this is the height machine theorem. It's a homomorphism from geometry to arithmetic. So geometry to arithmetic. It says there exists a unique homomorphism actually this fact that homomorphism, it's a new statement, which I haven't, this is some kind of a curly H from Picard of X. Think of divisors up to linear equivalence or isomorphism classes of line bundles. To R to the xk bar. So think of functions from xk bar to real numbers. These are the heights that I want to capture. But modulo bounded functions. And I actually like this notation because it is clear. So I'm talking about bounded functions as a subset of this set, which means bounded as you vary your point in xk bar. It's a homomorphism. That's a new information. So if you look at summation of two divisors, it's going to go to the summation of the two functions. It's with the property that, so there exists a unique homomorphism of this form. I essentially gave you the construction without proofs, how to do it. You give me a line bundle or divisor. I will write it as difference of two ample ones, and I do that. And the theorem, the statement was that they are well-defined up to only bounded functions. So I have given you an outline of how one goes and proves or checks all the details. This unique homomorphism has this property that you also verify, that if you start with the ample line bundle, or let's go very ample, then the function that you get up to bounded functions is what you expect. Phi sub L, which is the map you get from the very ample divisor, matches H of x comma L up to bounded functions. That's already in my notation. So essentially, it's this extra property saying that it's the function I was describing. Up to bounded functions, it's the function you expect, the composition of the naive height on projective space composed with the map that you have. And it's not only it exists and it's unique, then you can also complete your theorem by saying it also has, moreover, it has some nice properties, which I want to write two of them. Moreover, there's a long list, but I'll write only two of them. It's functorial, which means if you have a map, I'm using phi too many times, let's put f from x to y. And if you have a line bundle here, or divisor here, then you can think of the height function of y with respect to L. And you can also think of height function of x with respect to pullback of L. And these two height functions match. I have to compose one with, what should I do? Height function here is going to be composed with f. No? Yes. They're equal. If I have a point in x, I can bring it in y, compute the height, or I can just compute the height on x. Is it okay? I'm close to the board. Do you see a mistake that I don't see? And then positivity is actually weird. It says, so positivity. You cannot expect a nice positivity statement because everything is defined up to a constant, up to a bounded function. What does it mean something is positive up to a bounded function? It just means it's lower bounded. So if base locus of the line bundle if you assume it's not the entire x, then height is, it's not positive, but it's positive up to a bounded function. So it's a weird statement. It's actually on x minus b, on places that you can put things on the projective space nicely. And then there is a long list. I should say, if you want to learn more about this classical theory, there are two books that you can refer to. One of them is by Henry and Silverman. I think there are multiple books together, but this is on Diophantine geometry. And then there is also a book by Gubler and Bombieri, which is called Heights. It's like 700 pages about heights, which I will say in 30 minutes. But I mean, these are relatively basic statements at the beginning. Yes, Oliver.
I'm confused about something. I think it was asked before. If taking automorphism of Pn, this shouldn't preserve the height, right? You can say.
Yes, but up to a bounded function. So it's going to be a different height function, but the theorem, which one should verify, is that
if you send, I mean, the automorphism of Pn is transitive, so you can send the point with very small height to any other point, which might be
yes. Yes, but I'm saying the height function that you get up to a bounded function, it's going to be the same. I'm not saying you get the same function. I'm saying you're going to get two different numbers, height changes. But as you vary in your space, your two functions are going to be not far from each other, which is a very weird statement. You should be suspicious. How is it even useful? So let's kill this O of 1. But you can't do better than this in general. You cannot do better than this in general. It's not because people haven't tried. Yes, more question?
Yeah, different. The second question, this x in your theorem, should this always be protected? Or
I have assumed for the purpose of these lectures not to give the most general thing because I want to talk about abelian varieties. So think abelian varieties. Projective smooth. You don't need all the words. And certainly 700 pages of book looks at more general situations as well. In fact, right now I want to go to abelian varieties next, which is the focus of this talk, and some of the most spectacular applications of height theory have been in the context of abelian varieties anyway. And these applications are not just from old times. There are versions of improvements of Falting's theorem, Mordell conjecture, which gives uniform bounds, and they work with the function that I'm going to describe next. There was another.
Yeah, one quick question, one last quick question. Can we say anything about the kernel of the homomorphism?
Kernel. What? Pick 0, yes. Pick 0 is included. Is it equal, or maybe Jose knows? Pick 0 is a good enough answer, I think, for me to move on, but I'm not sure if it's equal. If you have line bundles that have first rank class 0, you get a height function which is 0. Again, for my applications, I'm going to be working with concrete divisors. And let me move on. So canonical heights. Now I'm going to assume X is, in fact, a abelian variety. So it's a connected projective algebraic group. Connected projective algebraic group. A good example is, of course, elliptic curves in dimension 1. And I know many of the people in this audience, including tropically minded people, know Jacobians. Jacobians are important examples of these, and I'll focus on them at some point. So the goal or the philosophy is exploit the group structure. Now you have a group, and try to make things nicer. That group should be useful. In fact, I want to get rid of this O of 1 that has been annoying, presumably everyone, certainly me. And I'm going to work with some specific divisor because I get a very nice function. I don't have to, but for these lectures, it's OK to take my line bundle or divisor to be effective or ample. And symmetric. Both of these are not absolutely necessary for the construction I'm going to describe, but the function that I want to work with is particularly nice when you have these properties. What is symmetric? For abelian varieties, you have group. You have multiplication by -1. So you can imagine what symmetric should be. You have the multiplication by -1 map from A to A. And you would require that if you pull back your divisor, you get something equivalent to your divisor. Or in the language of line bundle, the pullback should be isomorphic to the original line bundle. It's some notion of symmetry which hopefully makes sense from your intuition on symmetry. So the idea of Néron and Tate is, I'm going now to 60s. I guess the original height machine, the way that they wrote it down is earlier, probably, I don't know, 30s, 40s. In 60s, Néron and Tate had the idea of getting rid of this pesky O of 1. So Néron and Tate, it wasn't a joint work, but certainly they were aware of each other's work. So idea is use the group structure, the group operations, to get rid of, among other things, you get rid of many bad things, but the obvious thing I've said so far is this bounded functions, O of 1s. Okay, let's look at multiplication by m now. I'm going to say what Tate did, and then I'll focus later on the technique of Néron, which is more relevant to tropical stuff. So this is multiplication by m. At the level of points, x goes to m plus m, x plus x plus x plus x m times. Since I have assumed my divisor is symmetric, you can check, or one can check, that if you pull back a symmetric divisor along this multiplication by m, you get something which is m squared times the original divisor. Even if it's not symmetric, you can give a formula about how the pullback works. You can, I'm not going to write it down, but there's a general computation you can do. But let's do an exercise. I have been sort of talking about theory, but now already with the stuff that I have, I can ask a very natural question. What is height? Take one of those heights that the machine gives. With respect to the divisor d of the p plus p plus p m times. So if I look at the m times a point, how complicated that point is. And you can actually do this on a computer. You can pick your elliptic curve, figure out what the group law is. They're usually given by some explicit formulas in terms of polynomials. Take a point on your elliptic curve and just add it to itself. And then you get another point, and you can see how your denominators are growing, how more complicated things are getting, how fast the numerator and denominator is getting bigger. Okay, and you can do it multiple times and start making a conjecture. And let's see what you should expect. So by functoriality, and this is, by the way, I'm not doing this exercise just for fun. It's related to the idea of Tate, how to get rid of the O of 1. By functoriality, so I have this map. I have a divisor here, or I'm going to think of my divisor here. It's going to be the pullback of the divisor. So I'm thinking of this as a point here. I'm bringing it back here. Up to O of 1, up to a bounded function. But then I just said, let's call this star. By star, if your divisor is equivalent to another divisor, you should get the same function up to another O of 1. So you get m squared d of p up to an updated O of 1. Now you have O of 1 first, O of 1 second, add them, you get another O of 1. And then this is by the fact that it's a homomorphism, this is d plus d plus d plus d m squared time. It should go to the summation of the functions. So you get m squared hd of p plus yet another O of 1. And I kind of answered the question that you could simulate and see. M times P up to this pesky O of 1 is M squared more complicated than P. So if you actually do this computation, you see your numerator and denominators are roughly growing at rate M squared. The number of bits that you would need to write it down. Okay, but so the idea now is, and immediately we'll see an open problem. The idea of Tate was that you should be able to kill O of 1 by taking a limit of this identity. It's called Tate's trick. So Tate's trick is saying that let's look at limit. Actually, let's take m equal to 2. It turns out any m that you pick is going to do the same job for you. You can pick m equal to 3. Just for concreteness, I'm going to pick m equal to 2. I'm going to pick one of these functions that the height machine is giving me and look at repeated powers, repeated applications of the multiplication by 2. And then I expect this to be, let's say n is equal to 1. It's going to be 4 times more complicated. I'm going to divide it by 4. And since I'm doing it n times, I'm going to divide it by 4 to the n. And take limit as n goes to infinity. And I'm going to define this. Well, it's actually totally unclear that this limit exists. Because, so by looking at this identity, you're seeing that I'm trying to divide everything by m squared and then take something like m to infinity. And I'm hoping that O of 1 divided by m squared, m goes to infinity, becomes 0. But it's not clear because I don't know much about O of 1, except that it's bounded as I vary among points. So it shouldn't be obvious, and it is not obvious. That's why Tate has a name on it, that this will die, magically will die. So that's what's happening. So this was probably an inspiration, but so Tate showed this converges. And how did he show that? I'm putting exclamation marks because it's not obvious. The way he showed it was both clever but also disappointing. He showed that this sequence is Cauchy. And then real numbers are complete, so Cauchy sequences converge. And I'm saying it is disappointing because it doesn't say anything about what it converges to. And in fact, it's a major open problem. Whenever this height is not 0, we don't know anything about it. We don't even know, I think we don't know. OK, so this is being videotaped, but I'm going to be brave. I've heard from experts, I won't name names, that we don't even know examples of a non-zero, non-algebraic number that you get. So one brave person might say these are always transcendental or something. It's a result from 2023 of a student of Yuan. I think his name is Yang. We have someone from the research group who proves that in function field case, everything I'm saying can be done not over number fields, but also function fields. In slightly more generality, these numbers are always rational. And that's actually related to something I'm going to talk about later this week. In function field case. In number field case, it's complete untouched territory. Okay? So the idea, the reason we don't know much is that by showing, and this is a clever computation, which again I've covered in a course. It's not deep, but so let's call this sequence AN. AN is Cauchy. Is it AU? I'm almost embarrassed. OK.
It's clear that it's non-zero?
I'll say that. So positivity now says because I killed O of 1, positivity says that it's bigger than or equal to 0. And it's relatively elementary to show that it's 0 if and only if you have a torsion point. I'm going to write it down. So whenever it's non-zero, I was saying we don't know much about what kind of numbers you get. But nonetheless, existence of this canonical height, which now does not depend on choices, except for fixing a divisor, has been very useful for all sorts of number theory problems, because abelian varieties are important. Even if you care about curves, there's a Jacobian that you work with. And that's how Voigt's proof and recent improvements of Falting's theorem go by. So let me just...
Sorry, is 2 crucial here? Number? Yeah, 2 is crucial there. So 2, the number 2 is crucial there?
No. If you take 3, you get the same function. If you put m, you get the same. That doesn't depend on. So doesn't depend on m equal to 2 choice that I made. You always get the same function. So what I said, I didn't write down. This is bigger than or equal to 0. It more or less follows from the property of the height machine. An elementary fact, once you have the construction, is that it's 0 if and only if P is torsion. And torsion, I mean in the sense of basic algebra. There exists some number such that that multiple of P is 0 inside your group. Okay.
Instead of repeated applications of m, we just take all m.
I picked m equal to 2 and then looked at repeated application of multiplication by 2.
You can also take
M goes to infinity.
m go to infinity. That doesn't work.
The trick that at least the proof of the Cauchy that I have in mind, it's,
Repeated application.
I certainly know how to do it when you repeated application of the same thing, but I suspect one can work harder and take m to infinity. Soon, yes.
I think it's 50 minutes now. You can go.
Did you say 1 hour or?
Well, it's 50 minutes. I was mistaken, I guess, as well. It's 50 minutes. I'm sorry.
What time should I stop?
Well, it was 11:40, but we can go a bit later.
No, but you told me 1 hour before
Yeah,
that.
I was mistaken. I'm sorry about
Okay, oh, okay. Okay. All right, let me actually, okay, so I won't say the connection to Arkelov geometry till tomorrow, but let me just end by saying that, okay, I made a function, but one should worry about, and nobody has been yet, is this still arithmetically interesting? Is arithmetically interesting? Does it have Northcott property type results? And the answer is yes, because it is essentially, again, up to a bounded function, is what I had already claimed is arithmetically interesting. It's one choice in that equivalence class that incidentally doesn't come directly from a line bundle, but it comes from a limit of such things. And then it's a quadratic function, and this is crucially interesting, meaning that if you look at m times p, you get on the nose m squared. It means a certain lattice that you can construct is actually sort of, it has a quadratic function on it. You can actually do linear algebra in the sense of inner product space. You can put inner products on some space of rational points. And maybe I won't list everything, but this is essential in Voigt's proof of Mordell. Also, more recent results due to Dimitrov, Gao, Habecker, and Kuhne on bounded versions of uniform versions of Falting's theorem. Okay, so let me just wrap up by saying I will talk about a local version of that, the same way that, so I haven't really been focused on non-Archimedean fields and things like that. The issue is I have given you a global number, but I want to factorize it soon. Just like 6 is 2 times 3, it would be nice to always have these global numbers to have local contributions. And from there, first of all, some connections with oracle of geometry I'll mention without details. But also, when you want to compute the local contributions, it turns out tropical geometry and Berkovich spaces will be crucial. So tomorrow's plan is mostly talk about Berkovich spaces, but I'll introduce the local version of this briefly, and then go from there. Thank you.